Okay, we're going to continue on here, chapter 11, and kind of finish up what we've been talking about. So we're kind of in the middle of electron configuration. So we're going to run through some of these examples here, and then we'll kind of review as we're doing it. So when we write electron configuration, remember there's pretty much a couple things that you need to know, which is obviously the order at which electrons go into the atom, and pretty much how many electrons each orbital or subshell can maximally hold. And in the case of an s orbital, there's only one type of s orbital, which means each individual orbital can hold 2 electrons. So on any energy level, if there's an s, it can only hold a maximum of 2. Because there are 3 different types of p orbitals, that is what is sometimes referred to as a subshell or sublevel. Each of those orbitals can hold 2 electrons, which means if you fill up a p subshell on any energy level, it's going to hold 6. And that's going to be 10 for our d subshell, as there's 5 different d orbitals. On any level, there are d's. And f's, which are the last ones, there are 7 different ones. So 14 maximum electrons. The order at which they go into the atom is something that you can recreate for yourself pretty easily by remembering what we talked about, that on the first energy level, which is what this first number represents, that principal quantum number, that is where we find only s orbitals. It doesn't happen until we get to the second energy level that p's start to develop, then the third energy level that d's start to develop, and then the fourth energy level is where we first start to see our f's. So if you just kind of remember that order and kind of put them diagonal of each other, all you have to do is pretty much just fill in the numbers underneath. And honestly, even if you go a little too far in terms of numbers at this end, you'll never get there anyways, probably in most cases, so you'll be okay. And you'll be able to write pretty much any type of electron configuration that you need to do. So for example, here, if we looked at beryllium, which is 4, remember that we always start up here at the top, and we would come here, which could hold 2. We would then need to swing back and come here to our second s orbitals, and in that case would give us an electron configuration of 1s2, 2s2. That is 2 electrons on the first energy level, 2 electrons on the second energy level, with the top number being how many electrons there are in each of the orbitals or subshells there are, and the first number being, again, really the principal quantum number, which is a fancy word for energy level, basically. We also talked about drawing what is referred to as orbital diagram. And in orbital diagram, we use boxes or lines to represent each of the individual orbitals. And we do use an arrow to represent the electrons. When it does go into the orbital first, it does go in the upwards position, which is sometimes referred to as having positive half of the spin. And when we put the next one in, Pauli's exclusion rule is basically the idea that they will have to be what's referred to as being paired, which means the second one comes in downward, which has minus a half spin. And that arrangement of electrons heading in opposite direction is what is referred to again as paired spin. The next one would go up, and the last one there would go down. And again, that's what's sometimes referred to as orbital diagram. If you drew it correctly in terms of energy, the second box would be higher than the first. I'm just obviously don't have a lot of room to do that, so I'm just going to go sideways in terms of that. Question on that there. Yeah, so when you go into the orbital, the first arrow should always point up. And then if you need to put a second one in the same box or same orbital, it has to go in the opposite direction, which is down. So they basically go in first up and then kind of come back in pair. Do they always have to be filled? They don't, if that's your question. So they don't all have to be filled. It's just however many electrons that you basically have. Another question on that. So let's take a look at a few more here, and then we'll kind of see how the rest fill in. So boron, which is 5, which has 5 protons, also 5 electrons. So once again here, we would start up here. We would come here, which could hold 2. We would zigzag back down. That could hold 2, but we actually need 5 in this case. So we will need to get into the p subshell here. And if we wrote the electron configuration, once again, it would be 1s2, 2s2, and 2p1. This means that we have 2 electrons on the lower energy level, the first energy level. We actually have a grand total of 3 electrons, those 3 on the second energy level, which is a higher energy level here. And if we were to do the orbital diagram for this guy, we would have our boxes for our S's. We would have 3 boxes for our p subshell because this represents px, the py orbital, and the pz orbital here. And the way the electrons would feel is, again, first one would go up, second one would go down, first one would go up, second one would go down. Now, in the terms of the subshell here, the next electron will go in the first one, which is the px, and again, it will go in that upwards position as it is the first one basically in the orbital. So the first one always in each orbital will have the plus half spin and basically represented by pointing the arrow in the upwards direction. Question on that one? So when we get to a subshell like what we're looking at with P, where we have multiple orbitals in a particular subshell, there are some rules that govern sort of where the next electrons go. And Hund's rule is sort of the rule that tells us where we should put our next electron. And our option would be really, we could put it next door. We could also put it into the same orbital. And the idea of Hund's rule is the greatest stability happens when we have parallel spin. And paired spin is when they're heading in opposite directions. Parallel spins means that they would be heading in the same direction. So based on Hund's rule, the best way to do it would be to put another one going in the same direction in the orbital next to it. Again, if we put it in the first orbital, that would pair off our spins, which would not be good according to Hund's rule here. So this rule basically states that when you get to basically P subshells, D subshells, or F subshells, where there are multiple orbitals that make up that subshell, they pretty much go in one at a time until you pretty much can't put any more in, and then they come back and we'll start pairing up afterwards. So that is how we basically fill the electrons within a subshell one at a time in the upwards direction to maximize the parallel spin. And then when you have no more room, we come back and pair it up. So if we look here at carbon, which is 6, once again, we would start here. That's going to give us 2. That's going to give us 4. And once again, here we will get into our 2p subshell. And once again, you don't have to fill it up completely. So it would be 1s2, 2s2, 2p2. Once again, 2 electrons on the first energy level. We're now up to 4 electrons on the second energy level, a couple in the s orbital, a couple in the p orbital. And again, our orbital diagram will look like this. First one goes in up, second one down, up, down. And now we will maximize that parallel spin by putting, again, one at a time. Obviously, we have room to go one more before we'll have to start sort of pairing up in terms of this P subshell. Excuse me. Any questions on that one there? All right, so let's take a look at the rest of this first 10. We look at nitrogen, which once again, we're going to start here. That will get us 2. That will give us 4. And we could get the rest of the we need here in our 2p subshell. So the electron configuration here for nitrogen will be 1s2, 2s2, 2p3. Once again, 5 on the second energy level and 2 in the first. Orbital diagram going to now basically maximize as much of that parallel spin as we can. Up and down, up and down. And now we should have 3 all pointing in the upwards direction. Our P subshell could still hold 3 more electrons, but at this point, we will have to now come back and start pairing everybody up. By pairing up the first guy and the next one, that will still create as much of the parallel spin or maximize as much parallel spin as possible. Question on that one there. So finish out the first 10 here. Oxygen, which is 8. Once again, our electron configuration, 1s2, 2s2, 2p4. Again, if you count the top numbers, 4, 6, 8 is how many electrons that we put in there. At this point, we have 6 electrons in the second energy level. And if we were going to do our orbital diagram, at this point, as we just talked about, we would now need to start pairing guys up here in our P subshell, but they would still go in one at a time. And we will pair up back here at the very first box, which really represents the px orbital in this case. Here we still have those 2 unpaired electrons in the other orbitals, again maximizing that sort of parallel spin that we could get in this situation. Question on that one there. And number 9, which is our fluorine, since we still have room in that P subshell, 1s2, 2s2, 2p5, giving us 7 in the second energy level and 2 in the first. And our orbital diagram at this point will go 1 up, 1 down, 1 up, 1 down. Once again, they will go in upwards first and now pairing. And as you can see here, we have space for 1 more electron in that subshell before we would have to move on. And it is completely filled. Question on that one there. So might as well fill it up here with helium, our neon, which gets us there at 10, which would be 1s2, 2s2, 2p6, giving us 8 electrons on the second energy level. And at this point here, we will fill up our orbitals. Once again, this guy will fill in this direction 1 at a time and coming back and now completely pairing off. At this point, if we had more electrons, we would have to go to the 3s2 in this case. Again, electrons go in 1 at a time, lowest energy until they're filled. And again, you don't have to fill up all the boxes. You just need to fill them up in the correct order and place as many electrons as you need. Question on any of those there. All right, so why don't you write the electron configuration for argon? So let's take a look. So we have 18 on this one. So starting here, that's going to give us 2. Coming this way will give us 4 total. Coming this way, we could put 6, which will give us 10. We then would have to come here, which would give us 12. Next one, we would have to come here, which would give us the rest of them that we need. So we would have to go all the way to that spot right there. And that's going to give us an electron configuration of 1s2, 2s2, 2p6, 3s2, 3p6. Once again, if you count up the top numbers, that is how many electrons total you placed. In that case, it's 18. Remember that that's the proper way to write it. No dashes, commas, weird things that people like to put. The electron should be a superscript up on top. Yeah, not a big number or anything like that. Our orbital diagram here, we'd obviously need our appropriate boxes for our different orbitals, but it would fill 1 up, 1 down, 1 up, 1 down. This guy, once again, would go 1 at a time and then come back and fill. This guy would go up and down, and this guy here would also, again, go 1 at a time and then come back up and fill in this case. Any questions on that there? So electrons do go into the atom, very similar to how the nucleus builds up protons, basically 1 at a time. Again, as we've been talking about, they are filled from lowest energy to highest. And that is the way that we write electron configuration, which is sometimes referred to as filling order, which is how they come into the atom. Sometimes people will write it based on energy, very rarely for our classes, but you should always write it based on filling, which is basically that zigzag pattern that we've been looking at. So if we look at something like potassium, which is 19, and we write the electron configuration for potassium, a couple things. Remember that it is going to be the 4s before the 3d, so that is lower in energy. So those electrons, once again, will go into the 4s before they fill up that 3d. So if we look at this part of the configuration up into here, that is 18 electrons. And as we just saw in the previous example, 18 electrons is argon. So you could do sort of a shorthand in the electron configuration. For example, something like potassium can be written like this, where you put a bracket around argon, and that represents basically argon's configuration. And then you continue on with the electron configuration. It does need to be a noble gas. So when you do this sort of shorthand, sometimes people refer to it as noble gas configuration. It has to be that noble gas that comes right before it on the periodic table. So if we looked at something like sodium, which is 11, 1s2, 2s2, 2p6, 3s1. This part of its configuration is 10 electrons. Thank you. Which is basically neon's configuration. So you could shorthand it neon 3s1. So if you want to do sort of a shorthand, it's very commonly written like that. You always want to go back to the noble gas on the periodic table that comes right before it. You put that in sort of brackets, and that represents its configuration. And then you continue on. Any questions on electron configuration there? Also, when things do gain charges, right, and we have ions, especially for representative elements, either a cation, which is positively charged, or an anion, which is negatively charged, you do have to adjust the electron configuration for those things. So if we look at something like oxygen with no charges, we just saw 1s2, 2s2, 2p4. When oxygen gains a charge, it is going to be -2, and that means that it will have 10 electrons in that case instead of 8, as it gained 2. And its configuration would be 1s2, 2s2, 2p6, which is 10 electrons are really the same electron configuration as neon. If we look at something like our sodium that I just wrote, has 11 electrons, which is 1s2, 2s2, 2p6, 3s1. When it loses electrons, it will be a +1 charge, which means it has lost 1 electron, and that means it has 10 electrons, which means its electron configuration would be 1s2, 2s2, 2p6, or neon's configuration. As you can see here, representative elements, like we talked about when we did bonding, will gain and lose electrons so that they end up in noble gas configuration. So if we look at the configuration of neon, oxide, and sodium, they all have the same electron configuration, which means they're isoelectronic with each other. They have the same exact electron configuration. And that, again, is the purpose of all bonding, as we talked about, is for everybody to achieve the same electron configuration as the noble gases, as they are very stable. Remember that they're not changing into those noble gases, but their electrons are basically going to be arranged just like a noble gas. And that's because the only way they could change into those elements is you would have to change protons, which is not what happens here when we gain and lose electrons, right? It's just the electrons being changed. So there are things that are isoelectronic, representative elements, which are guys sort of on the side, outside of the transition metal region. When they lose and gain electrons, they will end up with the same electron configurations that noble gases. So nonmetals will gain electrons, go forward on the periodic table to the noble gas that comes after them. And metals, like we talked about with bonding, will lose electrons and back up on the periodic table to the noble gas that comes right before them. And again, that's pretty much the purpose of all types of bonding, as we talked about. Ionic, covalent bonding is for everybody to get that same electron configuration as the noble gases. Question on things with charges. So you do have to adjust the electron configuration for the charge, either add or subtract. And again, if it's a positive charge, it obviously lost electrons equal to the charge number. And if it's negative, it gained electrons equal to the charge number. Any questions on that? So transition metals are a little bit different in terms of how things occur with them. So let's talk a little bit about transition metals and what happens with their electron configuration. Transition metals really do not start until the D subshells, which is the third energy level. And they have completely filled D subshells or filled D subshells. Now, there are a few exceptions in terms of the normal electron configuration. In fact, there's a lot actually, but if you follow that sort of zigzag thing that we created, there are a few exceptions to the proper electron configuration. The two notable ones that usually you have to learn for chemistry are these two in the first row, which is chromium and copper. So if you were to follow the zigzag approach there for chromium, you would end up with argon 4s2 3d4. And it's been found experimentally to actually have one more electron up in the d orbital and one less electron in the s orbital. And the proper configuration, as you can see down here for chromium, 4s1 3d5, that maximizes the d orbital with parallel spin, an electron in each of them, including a parallel electron there on the s. Copper is a similar thing. Instead of 4s2, what it normally would be 4s2 3d9. It also has one more electron up there in the d, one less electron up in the s. This is possible because these orbitals here are super close in energy. They're very close in energy, so it doesn't take a lot for electrons to sort of bounce up into the d orbitals. So it's very easy. In addition, when you start filling the actual d orbitals with electrons, what actually happens is these guys actually switch in energy. And you end up with the 4s orbital actually being higher in energy once you start filling in sort of the d orbital. So there's actually that switch. And that's also why sometimes if you look up online or something like that, you will see sometimes people write electron configuration like all in order, like all the threes together, all the fours together. And that's based on energy after the electrons have gone in there and you have that switch in the orbitals. You should not do that in this class or probably any chemistry class that you take. I've only had one in my whole life, I think, that's done it that other way. Everybody usually writes it in the filling order, which is that kind of zigzag move that we've been using. But they actually do switch energy or transition metals, those orbitals, once they start filling the d orbitals. Question on that. In addition to those on chromium and copper, if you look on the periodic table, pretty much where chromium and copper are located, you come down and left and right. There's a ton of exceptions to the normal electron configuration. Like silver, PD has like no electrons in the s. So there's a lot of exceptions underneath chromium and copper if you go down and in. For us and most of your chemistry classes, chromium and copper are the ones you have to worry about. These are just the exceptions. Yeah, so for us, you'll be responsible for, like I said, most classes you take, it's like these two. This is usually the one they usually talk about. So we'll be responsible for that. You should just know that underneath there are a lot of exceptions that sort of occur there. But for our class, you could just write it like from the zigzag thing and it'll be okay, even though technically it is sort of an exception of those. But chromium and copper are the two that you do need to know the exceptions for. And again, they're both pretty similar in exceptions, just one extra electron up there in the d orbital and one less in the s. So the correct one there is on the right that I circled. Those are electron configuration you should use for those two. Yeah. This one or yeah. So question on that there. Now, looking at this slide as well, when transition metals actually lose electrons, they actually do lose electrons a little bit differently than how representative elements do. And it has a lot to do with what we see on this slide, actually. Because you have this sort of switch in energy that occurs once you start populating the d orbitals, when transition metals actually lose electrons, say something like iron, which is 26 there, I think. And that would be argon 4s2 3d6. Because there's a switch in the energy of those orbitals, when iron, for example, becomes +2 charged, that has 24 electrons, the higher electrons are actually going to be those s electrons, and the transition metals will always lose their s electrons first. So the proper configuration for iron with a +2 charge is argon 3d6, as we're going to get rid of these two. So that sometimes throws people because they just kind of take it out of the last one. But technically speaking here, our 4s are going to end up being higher in energy. So they will come out of there first. Also different for transition metals is if it needs to then, for example, if it had a +3 charge, it would have 3 less electrons. If it already uses up all the s's, it then will dig into the d's at that point, and then we would need to take 1 out of the d, and that would end up as argon 3d5. So transition metals are a little bit different than representative metals. They do not end up at a noble gas configuration because they have a long way to travel to get there, so they won't really end up there. But they will always lose the s's first, and then if necessary, you will dip into the d's to take out whatever electrons you would need to kind of finish out the electron configuration. Question on that there. Yeah. It is. So when the electrons go in, S is actually lower in energy, so it gets the electrons first. But once the d start to get electrons, those sets of orbitals basically switch energy, sort of levels, if you will. And the s ends up being higher in energy once the electrons are in the atom. And that's the point when they're going to lose their electrons, right? So at that point, those s's would be higher in energy and they would be lost. So that's basically what happens with transition metals. Always will dump those s's first and then go into the d's. Question on that there. So if you had something like nickel with a +4 charge, nickel with no charge is 28, which means it would be argon 4s2 3d8. Now, nickel with a +4 charge means it has 24 electrons. So the nickel here will lose 2 out of the s, but it still needs to lose 2 more. So then it will go to the next highest, which would be those d, and take 2 out of there. And you'll end up with argon 3d6 as the electron configuration for nickel with a +4 charge. So all the representative metals, you basically just take the electrons out of the last one that you wrote in the electron configuration. For transition metals, you kind of have to go one back to the s's and take them out of there first, and then into the d's that you need to. Any questions on transition metals and losing electrons? Obviously, they're metals, so they will only lose electrons, so they won't gain electrons or anything like that. Okay. Now, the lanthanide series, which is our guys on the bottom, that is where we get into our F's orbitals and electrons in our F orbitals, and they also have completely filled or incompletely filled F orbitals, and those are the 2 rows on the bottom there on the periodic table, are really the first bottom row there on the periodic table. Speaking of the periodic table and electron configuration, you can count off electron configuration from the periodic table if you know what you're doing and you're careful. There are periods on the periodic table which go this way. Those are the n numbers, like n equals 1, n equals 2, all the way through 7. And that's like the 1s1. The first 2 boxes here are columns or groups, are the s block, and there's 2 electrons, so that's 1 and 2. Group 3 through 8 is the P block, which can hold 6. 1, 2, 3, 4, 5, and 6. The D is 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, which comes from our transition metals. And our F down here is 14. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14. So if you wanted to kind of look and count off electron configuration here, let's just say we wanted to get over here to sodium, which is right about there. You would start here and go 1s2 to the end. This would be 2s2, 2p6, and 3s1 would be the electron configuration. Let's say we wanted to go over here to chlorine, which is about right there. Again, you would start at the top there and go 1s2, 2s2, 2p6, 3s2, and 3p, 1, 2, 3, 4, and 5. You literally can count it. You do have to be a little bit careful when you're doing it. And that is, let's just say we wanted to do our iron, which is right about here. That's our iron. It would be 1s2, 2s2, 2p6, 3s2, 3p6. Remember, it's 4s2, and this is 3d. That is the first energy level where d's appear. So that is not 4d, that's actually 3d. That would be 3d, 1, 2, 3, 4, 5, and 6. So if you're counting off on the periodic table, you do want to be careful because this is really 3d, 4d, 5d, 6d. And D's are 1 behind the period number. Also, these guys on the bottom, that's 4F, where F start, and 5F, which are 2, because they should go right about there. They are 2 behind the period number. So I would highly recommend perhaps just using the zigzag thing. You should get the right electron configuration. If you want to count it off the periodic table, you do have to be really careful, especially if you get into the transition metal region or even down on the bottom there, because there's a lot of off numbers from the period number. If you stick this stuff on the outside, pretty straightforward. You probably won't mess up, but definitely will be okay if you kind of use that zigzag approach. Question on using the periodic table to count electron configuration or electron configuration in general. Okay. Then let's talk a little bit about some periodic trends here officially and some of the reasons why we see what happens with, say, metals versus non-metals. First thing is valence electrons. As we know, valence electrons are the outermost electrons, the ones in the highest energy level, and they are the ones that are involved in bonding, right? So those are the ones that we see in bonding. And if we wrote the electron configuration for our nitrogen here, has 2 in the lower energy level, has 5 up here in the higher energy level. These would be as 5 valence electrons. The ones in the lower energy level are sometimes referred to as core electrons. They're the ones closer to the nucleus, held a lot tighter than valence electrons. And we'll talk about some of the reasons why they're not involved in bonding, but it is those valence electrons that are. We looked at sodium, 1s2, 2s2, 2p6, 3s1. These are core electrons here, and this is its 1 valence electron. So the valence electrons should be the highest energy electrons you have in your electron configuration, and you can write your electron configuration to figure them out. But as we talked about when we did Lewis structures, nobody wants to do that. So you can look at the periodic table and very easily figure out the number of valence electrons something has. It should be equal to the group number. So number of valence electrons equals the group number. So we looked at our sodium there. Sodium is group 1, it has 1 valence electron. Nitrogen is group 5, has 5 valence electrons. So that really is sort of the easiest way to figure out the number of valence electrons. A lot of people will say for transition metals that they have kind of 2 valence electrons, which are the S's, but some say they could have upwards of 12 because technically they could also go into the D's at that point. The good news is it doesn't deal too much with valence electrons from our transition metals, but you could look at the group number for everybody else. So carbon there, which is group 4, has 4 valence electrons. And again, if we looked at carbon's configuration, that would be the 4 valence electrons that we would see there for carbon. Questions on valence electrons there. So let's talk a little bit about some of these trends of metals and non-metals on the periodic table. As you know, from some earlier experiments that you did, reactivity of metals increase as you go left and down on the periodic table. Perhaps you saw calcium, lithium, potassium, one of those you saw some videos of, I think. And when you looked at the reactivity, it did increase as you go down. And we're going to talk about why that happens with some of these periodic trends. As you go up and to the right, that's where you find really your most reactive non-metal. So if you remember that experiment you did where you had the different layers and the halogens were jumping layers and the top hexane layer turned a certain color versus the bottom layer. What you saw in terms of reactivity as you go up group 7, for example, in reactivity increases. Chlorine is more reactive than bromine, which is more reactive than iodine. And obviously fluorine would be more reactive. So one of the reasons why we see that is an idea, bless you, of what is known as effective nuclear charge, which is sometimes abbreviated as Z effective. That is the positive charge that an electron feels due to what is referred to as shielding. So what does that mean? If we take somebody like lithium, which is 1s2, 2s1, lithium basically has a nucleus that has 3 protons in it. And on the first energy level, it's got a couple of electrons hanging out. I'll just draw them like that. On the second energy level, it's got an electron hanging out there. Now, these 2 electrons that are closer to the nucleus, which are our core electrons here, they basically have a front row seat to that +3 charge. And remember that when you look at charges of positive and negative things, when they come together, the higher the positive and negative charges, the stronger that association is. So something with a +3 and -3 will be held together stronger than a +1 and -1. So these guys are definitely feeling pretty much the full brunt of that +3 charge. When we look at the outer electron, our valence electron here, he's actually not going to experience that full brunt of the +3 charge. And that's because he's going to experience shielding. And what that basically means is these electrons are in front of him, which means they're taking on the full shot of the +3. So he's just getting a little bit that kind of passes by them. It's kind of like, again, if you go to the movies, you sit down, you got nice seats, you can see the screen perfectly. Somebody comes out with a giant hat and sits right in front of you, just shielded half of your screen, right? So you're not getting the full effect, obviously, of that movie. And the same thing sort of happens with the association here. We could actually calculate what is known as the effective nuclear charge by taking the atomic number, which would be +3, number of protons, and we could subtract from it the number of electrons that are shielding them, which are these 2 there in front of them, which means, effectively speaking, that outer electron is actually only feeling a +1 sort of attraction to the nucleus, which is a much weaker attraction than those 2 core electrons are feeling from the +3 charge. That means that those core electrons are going to be held a lot tighter than our valence electron, which is further out and not being pulled in as tightly to the nucleus charge there. And that's why when we think about bonding, the ones that are involved are the valence electrons, because they're not held as tightly for a lot of reasons. And that's one of the big reasons is this effective nuclear charge. When you go to the right and up on the periodic table, it increases and it decreases as you go down. And that's because as you go to the right on the periodic table, there are things with a lot more protons, right? So a lot more protons to start with means the nucleus has a greater positive charge, which means even the outer electrons are going to be pulled much closer because of that, as opposed to the guys on the left, which have less of a positive charge even more sort of electrons out there, not going to be pulled as tightly. Any questions on effective nuclear charge? Some other important sort of trends are ionization energy. Ionization energy is the energy required to remove an electron from the gas phase. And ionization energy is usually associated with cations, which are positively charged. And electrons actually come off one at a time. And metals have very low ionization energy, which is why they typically will get rid of their electrons pretty easily. And nonmetals have a very high ionization energy because, as we just talked about, even the furthest electrons are closer to the nucleus because of that effective nuclear charge, and they're feeling a much higher effective nuclear charge, and they're going to be held tighter. In general, for our first ionization energy, it increases as you go up and to the right on the periodic table, decreases as you go left and down on the periodic table. It does occur, as I mentioned, in sort of stages. So, for example, if we took something like magnesium, the first thing that would happen is magnesium would actually lose one electron. And that's what's referred to as the first ionization energy, the energy basically just to remove that first electron. Then magnesium with a +1 charge would lose a second electron. And that's known as the second ionization energy. And lastly, our magnesium here with a +3, perhaps +2, would lose one more, would be a +3. And that would be our third ionization energy. So every time you remove an electron, it requires a certain amount of energy, and that is what is referred to as first, second, third, however many electrons you're taking off of there. The trend between first ionization energy, second, and third, for example, is it gets much harder to remove electrons as you start to take one off. And that's because when we have a neutral atom and it loses an electron, the overall size shrinks, which means their outer electrons have just moved closer to the nucleus, and now they're going to be held tighter than they were a second ago. You lose another electron, gets even smaller, so those electrons keep moving closer and closer to the nucleus, which means it takes more and more energy to remove it. So typically speaking, the first ionization energy versus the second versus the third, it continues to increase as you go from each electron that you basically take off. Any questions on that? Yeah. It will do that. And at some point, though, the amount of energy required to remove additional electrons is not going to be really feasible, and it won't happen. So to answer your question, maybe if we look at actual values here and we see what happens for first, second, third ionization energy, when we look at something like magnesium, the first one to remove is about 735. To take off the second one, it's about 1400, about doubles in terms of energy, so much harder to remove the second. And now if we wanted to jump to the third, it's about almost a 6 to 7-fold increase in energy, which typically doesn't happen, which is why when we look at something like this step is not really favored, because at that point, you're into its core electrons. So once it gets really all those valence electrons out and it hits those kind of noble gas configuration, you're pretty much into the core electrons at that point. Energy-wise, nobody else is going to leave at that point because they're just held too tightly for them to remove. So that's why they kind of stop there. And that's why things like magnesium always forms a +2 charge, right? Because it's group 2. It's also why something like sodium, first electron to lose for sodium is this one, which is its valence electron. It is now Na+. To try to remove the second electron, which is in the core, and he's already at noble gas configuration, it's about a 10-fold increase in energy, which is never going to happen. And that's why something like sodium will just lay up there at +1 and stop losing electrons at that point. Questions on that? So typically, we do see that incremental increase in ionization energy through our valence electrons as we continue to lose electrons. Pretty much when you hit that core electrons, you're pretty much out of luck of trying to remove electrons, because at that point, everybody's pretty much squished on each other, and those outer electrons are now, which are those core electrons at this point, are going to be even closer to the nucleus and just not energy efficient to try to remove. Other questions? Let's talk a little bit about electron affinity. Electron affinity is the energy change that occurs when somebody gains an electron, and we associate this with anions or negatively charged. And the general trend on the periodic table is as you go up and to the right, electron affinity increases. And as you go down, it decreases. Not perfect trend. So for example, if you go up group 7, it increases and then the energy change kind of drops when you get to fluorine, but it's not a perfect trend, but that's the general trend. Not to be confused with electronegativity that we talked a lot about when we did bonding. And that's the ability, right, of an atom to bring electrons towards itself. And that also increases as we go up and to the right and decreases as you go down, with obviously fluorine being our most electronegative. So basically, as we can see here, as we go up and to the right, we have things that want to hang on to their electrons, want to take somebody else's electrons, and that's why we associate nonmetals as things that will gain electrons. Any questions on that there? And that's also why we see, as we go across the periodic table, the size starts to decrease and gets smaller. And as we go left and down, the size of everybody gets larger. And that has a lot to do with a lot of these trends that we talked about. By the way, we talked about what happens when somebody loses an electron. When somebody gains an electron, becomes negatively charged, the anion gets larger, right? Because it builds out more electrons in its sort of cloud, so it gets larger than the neutral guy. So as we go up and to the right on the periodic table, as we go this way, we have things with very high ionization energy. We have things with high electron affinity, high electronegativity, high effective nuclear charge. So all those trends basically are, we got things very close to the nucleus being held tighter, means lots of energy to try to remove them. They want to gain people's electrons and they don't want to give away theirs. And this is why we think about nonmetals as things that will gain electrons, right? And that's opposite as we come this way on the periodic table. We have things with low ionization energy, low electron affinity, low electronegativity, and lower Z effective nuclear charge. We have all these guys that are pretty large in size because those electrons aren't being held as tightly. Doesn't take a lot of convincing for them to give away their electrons, and they really have no interest in gaining electrons. They rather just get rid of their electrons. And this is why these guys are typically our metals, the ones that will lose electrons. Any questions on any of those periodic trends and how they tie together here? All right. So if we take a look at this, which one should be the larger atoms, sodium or chlorine? We look on the periodic table, sodium is further to the left than chlorine, which means chlorine should have all those trends that are going to bring electrons closer to the nucleus. And that means that sodium here should be the larger atom, as it's not going to be held as tightly, less of an effective nuclear charge, and less ionization energy. Any questions on that one? Which one is larger between lithium and cesium? They're in the same group on the periodic table. So as we go down a group, we see the size get larger because, again, has less ionization energy, less electron affinity, smaller Z effective. So in this case, it should be cesium that should be the one with the larger atom. And in this case, it is the, as it is there, the hydrogen 1s orbital is going to be the larger orbital versus the lithium. And you may say they're both 1s orbitals. Shouldn't they, which one should be larger or not? And it has a lot to do with the difference in the nucleus. So this is hydrogen, which has 1 proton. This is lithium that has 3 protons. So even though they are both a 1s orbital, that stronger attraction by the more positive lithium nucleus is going to pull the 1s orbital lower and closer, which means overall this size is going to be smaller than the guy on the left there is not going to feel as big of a pull. And when we think about which one is lower in energy, it would basically be the same answer there. Because lithium is going to pull that 1s orbital closer to the nucleus, it will actually be lower in energy than the 1s orbital that we find there in hydrogen, as it's not going to feel as strong of a pull by the smaller positive charge. Any questions on that? Yeah. Yeah, well, lithium would be larger in the sense we're here in this question. We're looking specifically at the 1s orbital, but lithium has 1s2, 2s1, which means no matter what hydrogen does, it doesn't have those extra electrons out there, right, in the second energy level. So that's why lithium overall is larger. But in comparison of their 1s orbitals to each other, because of the pull of the positive charge, they won't sit exactly in the same sort of spot relative to the nucleus. Yeah. Other questions? And obviously here to look at increasing ionization energy and atomic size, we look on the periodic table, that is the location of those three elements, sulfur, oxygen, and fluorine. And in terms of ionization energy, it does increase as you go up and to the right, which means ionization energy should increase up and over that way, which is what we have here. SOF should be the correct order in increasing ionization energy. And atomic size, remember, size gets smaller as we go this way. That means that as we go up and over, fluorine should be the smallest. So in increasing order, we would start with fluorine and end with sulfur in this case, which would be the largest, heading back that way. Any questions on any of these periodic trends here? So these trends really do explain why we see pretty much what we do see with metals and nonmetals, that the metals, again, typically are the ones going to lose their electrons and nonmetals are going to gain them. Also why when we get a metal and nonmetal together, we get the transfer of electrons because they have very different periodic trends. And that's why when we have two nonmetals together, which are close on the periodic table, the best they're going to do, because they both want to hang on to their electrons, is share electrons in covalent bonding. So that's why they share them as opposed to transfer them. Any questions on any of that there? All right, that wraps up chapter 11, I believe. So let's talk a little bit about those. So acids were first recognized by their sour taste, things like vinegar, which is acetic acid, there's citric acid there in lemons. Bases, on the other hand, have a bitter taste. They feel very slippery if you get it on your hand. I don't recommend it unless you're using soap, or I don't use the unclogging Drano on your hands or anything like that. But those guys are really bases. You could go like Home Depot and buy just straight sodium hydroxide. It comes with a lot of warnings of how to use it to unclog your drain. But they are bases. They are sometimes referred to as being alkaline, really. And alkaline, again, if you do come across that word, pretty much means basic. And that's why if you take a look at the periodic table in group 1 and group 2, group 1 are our alkali metals, group 2 are our alkaline earth metals. So a lot of strong bases come from group 1 and group 2 on the periodic table when you kind of hook those guys up with some hydroxide, potassium hydroxide, sodium hydroxide, calcium hydroxide. So a lot of those bases on the periodic table come from kind of group 1 and 2. Just for reference point, a lot of acids are actually nonmetals together, like NO2 or NO3 there with some water. Our CO2 and H2O will make carbonic acid. So a lot of acids are derived from nonmetals coming together, and a lot of bases are derived from group 1 and group 2 on the periodic table. Now, sort of a early definition was one done by Arrhenius. He did a lot of work with electrolytes, and if you remember, electrolytes are substances that go into a solution and completely break apart into ions, and they can conduct electricity, and it's the presence of those ions which help it conduct electricity. He defined an acid as the ability to produce hydrogen ions in solution And when we talk about something being an acid, it is the ability to produce free H plus ions in solution, not attached to anything, floating around in the solution. This is also a really good time to talk about in acid-base chemistry. You oftentimes will see H plus, you also see H3O plus. They are essentially the same. This is the hydrogen ion. This is the hydronium ion. They essentially mean the same in acid-base chemistry. They're used interchangeable in formulas, also chemical reactions and equations. I personally use H plus most of the time. A lot of people use H3O plus. So wherever I put H plus, you pretty much can swap it out for H3O plus in formulas, and it's basically the same thing. In addition, in acid-base chemistry, H plus is sometimes referred to as a proton, which is also another terminology that's sometimes used for it. And that is because hydrogen has one proton and one electron. In order for it to become positively charged, it had to lose its electron, and that left it just a proton, as it has no neutrons. So sometimes referred to as a proton. So if somebody says proton, H plus, hydronium ion, they're all talking about the same thing in acid-base chemistry. They're all talking about really the acid part of the solution. And even if it was H3O plus, you would have free H3O plus floating around in the solution. He defined a base as something that has hydroxide, and that's also the same deal. It is something that's able to produce free OH minus in the solution, floating around freely. As we'll talk about in this chapter, the sort of ratio of an OH minus in a solution basically will determine basic or neutral, depending on how much of those things that you have. Again, freely floating in the solution, not attached to anything else. So here, for example, is if we take some hydrogen chloride gas and bubble it through water, we will get our hydrochloric acid, which is HCl. Another reminder that which we talked about when we did naming, acids typically will have the aqueous symbol next to it. And that is because it's dissolved in water, and that is hydrochloric acid. And if you remember as well, when we talked about naming, hydro and ic is how we name acids that do not have oxygen. So that is hydrochloric acid. By the way, if it does have oxygen, it will have a polyatomic ion, if you remember right, and that would be nitrate, ATE, which means the acid here would be nitric acid, IC acid for anything that has 8 at the end of it. And if you had something like HNO2, that guy right there would be nitrite, ITE, polyatomic ion ends in OUS, acid. So just a reminder that if it has oxygen and it's an acid, we do not use hydro in the name, just for our guys that do not have oxygen. Nice review of that, I suppose. And obviously, if we take some sodium hydroxide here, it's going to break apart and produce some hydroxide, which is why this is considered a base. And its ability to produce that H plus in solution is why it is considered an acid. Question on that there. So the concept of the Arrhenius acid and base was a good one, but he did a lot of work with bases that include hydroxide. And not all bases actually have hydroxide in them. Most strong bases, which are strong electrolytes, have hydroxide in the formula, like sodium hydroxide, potassium hydroxide. But there are certain bases, for example, like ammonia, which is actually a weak base that can react with water, for example. And what's going to happen here is the water is actually going to donate an H plus over to the NH3, and it will make NH4 plus and OH minus. And because it's able to produce some hydroxide, it is still considered a base. It's also a weak base, as you might notice by the arrows heading in both directions, like we saw with weak electrolytes. It will have to go do a little reaction to do that. And that's why that's different than something like sodium hydroxide. which if you have this base, all it has to do is go for a swim, and you're going to break it apart 100% because this is a strong electrolyte. And you will have generated in that particular solution a ton of OH minus really quickly, which is why it's considered a strong base, because the amount of OH minus will go up tremendously fast when you put that sodium hydroxide in there. The amount of OH minus will also go up with the ammonia, but it'll be a lot less free OH minus in that solution, but it's still able to produce that. Questions on that there? So a more sort of general definition of acid and bases, and one most people think about when we talk about acid and bases, is what is referred to as the Bronsted-Lowry definition of an acid and base. And in a Bronsted-Lowry definition of an acid and base, an acid is something that will be a proton donor, and that's H+. So something that will give away the H+. And a base is something that will accept an H+ or a proton. So if we look at the reaction that we just saw there, our NH3 plus our water, in this case, it is the water donating the H+, which means in this case, water is our acid, and our NH3 is our base. And the definition of Bronsted-Lowry acid and base is it will actually create partners within the reaction. And if we look on the other side, this NH4 plus is the partner. It looks kind of like the NH3. And that is what is referred to as the conjugate acid. And the water on this side and the OH on this side is related to each other. And this is what is known as the conjugate base. So a base on one side of the reaction will have a partner on the other side of the reaction, which is known as its conjugate acid. And the acid on the left-hand side of the arrow will have a partner on the right-hand side of the arrow, which is known as its conjugate base. Regular acid and bases are found on the left-hand side of the arrow. Your conjugate acid and conjugate bases are found on the right-hand side of the arrow. The absolutely only difference between those two things is this H+ that has been transferred. So that should be the only difference between those two things. This guy will have one more H+. This guy will have one less H+. Now, if you look at something like the hydrochloric acid dissociating, a strong acid in water. In this case, our HCl is actually going to transfer the H+ over to the water, and that will create H3O+ and Cl-. In this case, it's actually the hydrochloric acid, surprisingly enough, being the acid. The water is actually acting as the base in this case, and it's going to make partners on the other side where this is the conjugate base. And these two guys here, that is our conjugate acid in this case. Once again, the only difference is that one H+ that has been transferred. And that has to be the only difference between an acid and conjugate base pair is one H+, only difference between the two. If there's anything other than that, they are not related to each other through this pair. First off, any questions on that? Now, earlier I said H3O+ and H+ are used interchangeable, and they especially are with acids. That HCl is a strong acid, which means what we're really looking at when we react it with water is it's really just breaking apart in water 100%. And you can represent that same equation on top as HCl gives you H+ and Cl-. So this is sort of a acceptable reaction or equation for the dissociation of this strong acid. In this case, I did not include water, so I got H+. Up here, I did include water, and I got H3O+. So that is really the difference as to why you get H3O+ versus just the H+. And it's actually acceptable to write the reaction either way. They both basically describe the same thing because they're both basically a strong acid. So I personally will probably write the middle one, but in most books, you'll probably see it written at the top. And you could think of it, it is really reacting with water, but it's really just the process of that strong acid breaking apart and releasing the H plus. That is what makes something an acid, right? Is the cation, which is the H plus, right? All acids, the cation is the H plus, and that is what is released to make it an acid. And it's able to do that in the case of a water. This also, bless you, demonstrates the idea of, in the case of the top equation, our water was a base. In the case of the bottom equation, our water was the acid. And there are certain things like water, for example, that could act as an acid or a base. And those things are what are referred to as being amphoteric. So an amphoteric substance can be so an amphoteric substance could act as an acid or a base like water can in that situation, and it's able to really go both ways. Any questions on that there? So if we look at our general sort of reaction here of our Bronsted-Lowry, this is a generic formula for an acid. And when we talk about acids, there's a few types of acids. There are what are referred to as being monoprotic, which means it has one hydrogen to give off, and that is abbreviated as HA. Here, the hydrogen is +1, the A is -1. An example of that in real life would be like hydrochloric acid is a monoprotic acid. It has one hydrogen to give. You could have something that is a diprotic acid. Diprotic acid has two hydrogens to give, and a generic formula would be this. Hydrogen still would be +1. The A here would actually be -2 charge. An example of that in real life is H2SO4. The sulfate has a -2 charge, and we need two hydrogens to balance it out. And you could also have a triprotic acid, which is sometimes abbreviated H3A. +1 for the hydrogen, -3 for the negative charge there, like phosphoric acid. Phosphate has a -3 charge. We need 3 H pluses to balance them out. So you sometimes have acids that could give away one hydrogen, like the case of HCl. It's basically this guy going to be given off into the solution as H plus. You could also have an acid that's an oxyacid, for example, like nitric acid, which I think we might have drew when we were doing Lewis structures. Looks something like this. And it's actually this hydrogen right here on that OH polar bond there that's actually going to come off for nitric acid. That's why it's still a monoprotic acid, as it just has that one hydrogen that it will be able to give off. So there's that example that we saw earlier, and our acid conjugate base pair relationship and our base conjugate acid. Once again, regular acid and base is left-hand side of the arrow, all your conjugate partners on the right-hand side of the arrow. And it's good to remember how they're related to each other. If you have an acid on one side, then you'll have a conjugate base on the other. And if you have a base on one side, its partner on the other side will be a conjugate acid, and again, only one H plus difference between them. And that is what's happening here. And this is, again, because water is involved, and really what's happening is that hydrogen being given off over here to water to form our hydronium ion in this particular case, which is our H3O plus. And it's because this will now be free flowing in the solution by itself is, again, what makes this an acid. All right, so let's take a look at these. So do each of these represent a conjugate acid-base pair? Let's take a look at the first one here. What we are looking for when we're trying to decide this is pretty much that. Is the only difference between these two things 1H plus? And again, it's important to remember that it's not just a hydrogen that you're either gaining or losing, but you do have that positive charge, which means If you lose an H plus, you become one more negative because you lost the positive. And if you gain an H plus, you now become one more positive because you gained the positive charge. So if we look at these two here, HClO4 and ClO4 minus, the only difference between these is one H plus. You can see that by taking away the hydrogen and taking away a positive makes it one more negative, and you end up with the guy on the right. Or just put the H plus on the guy on the right, you end up with the guy on the left. If we look at this one here, HCl and ClO minus, the difference between this is one H plus, but the problem with this is there's also a difference of an oxygen, which one does not have. So that is more than just one H plus difference, which means that this guy cannot be pairs because it can only be an H plus difference between them. If we look at our next one there, H2PO4 minus and HPO4 2 minus. Once again, the difference here is one H plus. If we take away an H, we're left with that. And because we become positive one lost, we become one more negative, and we end up with the same guy on both sides. So they are pairs. And obviously here, the only difference is one H plus, and they would be pairs. So it looks like 1, 3, and 4 here are pairs. So that has to be the only difference, and it's easy to recognize. Just either put it on, and you should end up with two things that look the same, or take it off, and you should end up with two things that look the same. Any questions on that there? All right, so finish it out here. Why don't you write the conjugate base for each of these? So what would be the formula of the conjugate base of each of the following? Okay, so since we're getting to the end, let's take a look at this and see. We want to write the conjugate base for each of the following. So if you're not really sure what you're dealing with, this is where sort of the Bronsted-Lowry sort of relationship is important to remember. Remember, we have an acid on one side and a base. And on the other side, we have a conjugate base and a conjugate acid. So the relationship is acid on one side, partner on the other side is the conjugate base, and the base on one side is partner on the other side is the conjugate acid. So in this case, if we are looking to end up with a conjugate base, if you just work your way backwards, you know that everything that you're looking at in this particular problem is actually an acid. And all you have to do at this point is use the definition of an acid, which is it will donate an H plus. So in this case, we actually want to take off the H plus for each of these, and that will give us the proper formula for our conjugate base. That means here, if we take off the H plus, we are left with one H and an S. It was neutral, so we lost a positive, so we become one negative here, and we should end up with HS minus. Here on the next one, we once again will lose a hydrogen, which leaves us an S. We also lost a positive charge, which means we get one more negative. And since it was already -1, it will now become -2 in this case. Any question on those two? So again, really important, the charge part of it, that you adjust it. People always screw it up and go the wrong way. Here's NH3. We're going to get rid of a hydrogen. That will leave us two hydrogens. And once again, here we have a neutral guy to start with. So it would become one more negative, which would be NH2 minus. And lastly, here we will lose one hydrogen, which leaves us an HSO3, and again, become one more negative here. And those would be our formulas of our conjugate base. So not in all problems, much like this one, will they tell you, hey, these are all acids or these are all bases. They'll just ask you, write the formula of the conjugate acid or conjugate base. So if you sort of think about